Welcome to this explainer. Today, we're focusing on one of the most famous and frankly most intimidating geological features on our planet, the origin and impact of the Yellowstone mega cauldron. We aren't just looking at the geysers and hot springs today. We're actually unpacking a deep Earth mystery. It's a mystery that connects a massive underground plume of magma to this incredibly tragic scene of buried dinosaurs hundreds of miles away. Our sources outline two very different scientific frameworks for understanding the exact same landscape, and we're going to see how they both interpret the clues hidden in the rocks.
Okay, let's dive right into this by asking our central question. Why is the visible scar that Yellowstone left across the North American continent so surprisingly short? I mean, really short. And maybe more importantly, how could that massive volcanic system possibly be responsible for wiping out entire colonies of baby dinosaurs up in Montana? To figure this whole thing out, we need to trace the evidence from deep underground all the way up to the fossil record.
But before we get into the competing theories, let's just make sure our essential geological vocabulary is locked in. First up, a caldera. This isn't your typical, cone-shaped mountain volcano. It's actually a massive crater formed when a magma chamber empties out and the ground above it just completely collapses inward. Yellowstone itself is a giant caldera. Second term, a hotspot track. Imagine a blowtorch fixed in place while you slowly slide a piece of metal over it. The burn marks left behind? That's a hotspot track. It's basically the chain of volcanic scars left on a tectonic plate as it drifts over a stationary, super hot plume from deep within the Earth.
Part 1. The Yellowstone mantle plume. So, deep beneath the crust, a massive column of anomalously hot rock, what we call a mantle plume, punches upward. But how and when did it actually become active? Well, here's where our sources diverge into two totally distinct frameworks. The Standard Model, which is the mainstream geological consensus, says that this plume operated really gradually over tens of millions of years, just slowly melting its way through the crust. But the alternative framework presented in our sources, called the Unified Theory of Geologic History, or UTGH, proposes something way more sudden. UTGH argues that a catastrophic planetary rupture event abruptly removed a protective subcrustal thermal buffer. And this sudden loss of pressure? It triggered rapid, violent decompression melting all at once, which launched Yellowstone's earliest and most violent eruptions.
Part 2. A decelerating tectonic plate. Now, what's really interesting about this is that when we look at the surface, where we can physically see the scar left behind, a really specific number stands out: 430 miles. That is the entire length of the Yellowstone hotspot track, stretching across the Snake River Plain in Idaho. Now, that might sound long, but in geology terms, it's actually incredibly short. Just for comparison, the hotspot track left by the Reunion plume over in the Indian Ocean is about 2,000 miles long. So why is Yellowstone's trail just a tiny fraction of that size? Once again, we look at how the two models interpret this anomaly. The Standard Model explains the short track through slow, uniform continental drift. Basically, the North American plate simply crept along at just a few centimeters per year. But the UTGH framework offers a radically different mechanical explanation. It claims the North American plate had been hydroplaning westward at catastrophic, incredibly high speeds following that initial rupture event. But it was running out of momentum and literally grinding to a halt right as it encountered the Yellowstone plume. Because the plate had already spent most of its kinetic energy, it was moving very slowly when it crossed the hotspot, resulting in this dramatically compressed 430-mile track. Part 3. The 80 million year gap. This timeline conflict becomes incredibly stark when we travel about 350 kilometers north to the dinosaur nesting grounds of the Two Medicine Formation in Montana. Mapping out the chronology here reveals a massive discrepancy. Under the Standard Model, the Maiasaura dinosaurs were nesting roughly 80 million years ago, but Yellowstone's first major eruptions didn't happen until about 2.1 million years ago. That leaves a massive 80 million year gap, meaning Yellowstone couldn't possibly be the source of the ash burying their nests. The UTGH framework, however, completely collapses this timeline. By rejecting the standard radiometric dating calendar, UTGH places both the dinosaur nesting and the massive first eruptions of Yellowstone in the exact same immediate post-rupture window. So under this model, that 80 million year gap vanishes entirely. Part 4. Burial of the Maiasaura. Let's zoom in on what actually happened on the ground, because the physical evidence here is devastatingly precise. The fossil record preserves this really tragic repeating cycle. Step 1. A massive eruption deposits a thick layer of ash across the nesting grounds. The adult dinosaurs survive it, but the young do not.
Step 2, the colony eventually recovers and actually returns to the exact same site to nest again. Step 3, the next major eruption happens, burying the next generation of hatchlings. The sources describe this with what they call a mournful precision, just layer after layer of ash, perfectly preserving the repeated death of the colony's young. And this brilliantly illustrates the core of the mystery. What volcano was producing all this ash? The rocks at Egg Mountain are packed with pale, fine-grained bentonitic ash. Geologically speaking, this points directly to a highly explosive, silica-rich, rhyolitic source. The sources note that Yellowstone is literally the only major volcanic system within a plausible transport distance, which is about 350 kilometers away, that's even capable of producing this specific type and volume of ash.
Part 5. The geochemical fingerprint. So how did the two frameworks resolve the identity of this killer volcano? Because the standard model separates the dinosaurs and Yellowstone by 80 million years, it has to look somewhere else. It suggests the ash came from unspecified subduction arc volcanics way off to the west. But our sources point out a pretty big problem with this. Arc volcanism typically produces dark and acidic ash, not the pale, silica-rich ash we actually find at the site. The UTH framework, having erased that time gap, argues that the ash is the direct fallout from Yellowstone's earliest and most violent plume-driven eruptions, blowing 350 kilometers north and burying those colonies. To prove this, the UTGHF framework actually makes a specific, testable prediction. If the ash came from the deep mantle plume of Yellowstone, rather than a standard continental arc volcano, it should contain a very specific trace element fingerprint. It predicts high levels of niobium and tantalum, elevated zirconium, hafnium, and yttrium, alongside highly specific isotopic values of strontium and neodymium. This isn't just theory, right? It's a precise chemical test that can be conducted on the ash layers to determine their true origin once and for all. When you connect these massive geological forces with the micro-level tragedy preserved in the rocks, you get this incredibly poignant quote from our sources. The Maiasaura at Egg Mountain were the first witnesses to what Yellowstone could do. It really anchors this huge macrogeological mystery into a deeply visceral scene of environmental impact. It transforms a discussion about tectonic plates and mantle plumes into a stark story about a living landscape reacting to immense subterranean violence. Which leaves us with this final, totally fascinating thought. We have identical physical evidence, right? A 430-mile volcanic track in Idaho and pale silica-rich ash burying dinosaur nests in Montana. Yet, depending on the framework you use to read that evidence, whether it's the deep-time gradualism of the standard model or the high-speed catastrophic compression of the UTGH framework, the story you uncover is entirely different. How is it that the exact same rocks and bones can tell such drastically different stories? It really makes you wonder just how much of our planet's history is still waiting to be reread. Thank you for joining me for this explainer, and keep questioning the ground beneath your feet.